delta x. Because it's a rectangle, and for a rectangle, the area is just a product of the sides. So this is an important thing which we have to know in advance, the area of the elementary piece. And after this, we take the sum, so let's call this area number I, and then we take the sum of this areas number I, from 1 to n. So let's say that there are n parts, n pieces in this partition. And the size of each of them is delta x. That's this delta x which I wrote here. So then this one, we take this as an approximation to the value of the area. And then the point is that as n goes to infinity, as the pieces become smaller and smaller, this approximation for functions satisfying some good properties like continuous functions is going to approximate this area better and better. And so the actual area we will get in the limit when n goes to infinity. And that's this integral. And so you recognize f of x dx as coming from this expression, f of x delta x, which corresponds to the area of this elementary rectangle. So there are some methods in mathematics which allow you to show that this limit actually exists, and so this therefore justifies this definition. And again, for that you actually have to make some assumptions on the function f. But all the functions which we'll consider in this course will satisfy this assumption, so I'm not going to talk about this. All right, so that's the second aspect, the definition. And finally, the third aspect is how do you actually compute it. So I purposefully separate this to points, the definition and the calculation, because the definition is rather complicated and in some sense esoteric, because you're breaking something in small pieces and so on. So this is sort of the hard part of the story, and but this is something which has been done. It has been proved that this process gives you a well-defined definition of the integral. And after that, we have to choose an efficient method to actually calculate this integral, and therefore calculate this area. We're not going to actually calculate things by actually breaking into pieces and taking the sum and taking the limit. We're not going to do that each time. In fact, we have a much more efficient method for calculating this integrals, and that's called the fundamental theorem of calculus, of one variable calculus, or a Leibniz-Newton formula. And that's the formula which tells you that to find this integral, you need to take the antiderivative. Where f of x is f prime of x. So in other words, to calculate the integral, you have to perform the operation which is opposite or reverse to the operation of differentiation. And it is in this sense that we can say that integration is reverse or opposite to differentiation. Something which is not at all obvious from the original definition as an area or as a limit of the partial sums, but which is nevertheless is one of the most important results here. And this is what we use in practice to calculate the integral. Okay? So I have summarized for you the story of integral of a function one variable. And in this course, we are dealing with functions in 2 and 3 variables. So of course, we're going to have integrals for such functions as well. Integrals for functions in 2 and 3 variables. And the structure of the story is very similar to the structure which I have just outlined. It also has essentially 3 parts. One is, what does it represent? 2 is, how do you define it? And 3, how do you compute it? Okay? So let's talk about functions in 2 variables. Now functions in 2 variables. A function in 2 variables also has a graph. So let's say you have function f of xy. Function in 2 variables also has a graph. And the graph now lives in 3 dimensions. So we draw a 3-dimensional coordinate system, where in addition to our variables x and y, we introduce one more variable, which we call z, right? So the next step is to realize what is the analog of this area under the graph. So here we're talking about the region which is bounded by the graph and the x-axis and this vertical lines. So there's a clear analog of this in the 2-dimensional case, right? Because in the 2-dimensional case, we can instead of the interval x from a to b, we can look at the rectangle where x is from a to b and y is from c to d. It's a rectangle. So let me draw it. So let's say this is x equal a, this is x equal b and this is x equal a, and then this will be y equals c and y equals d. So I'm talking about this rectangle. So this is a, this is b, this is c, and this is d, right? I'm talking about this rectangle. Don't confuse this rectangle with this rectangle, because they're both rectangles, but they have totally different meaning. In this rectangle, the variable is one side, and the other side corresponds to the function. And now we're just talking about the variables. Now we have 2 variables, so we have this rectangle on the xy plane. And now let's suppose that the function f of xy, our function, is non-negative on this rectangle. So that means that the graph of this function is going to lie above the xy plane if we look at the part of the graph corresponding to this rectangle. So what does it look like? So the way it's going to look is as follows. So let me draw first a kind of walls of this picture, and then so it's going to be something curvy above this rectangle. So let's say, it could look something like this. So this would be part of the graph above this rectangle. And the graph could continue, but we will only be interested in what happens above this rectangle. So now we clearly have a 3-dimensional region. Which is bounded by these walls. And the walls correspond to, so this would be dotted line. So the walls correspond to this vertical planes, which are obtained by taking the segments and kind of moving them vertically up. Right? So you got this 3-dimensional region bounded by those walls, by this rectangle at the bottom, and by the graph of the function at the top. And this 3-dimensional region is an analog for our function in 2 variables of this 2-dimensional region. And the integral of the function f will represent the volume of this 3-dimensional region. Right? So we've got this 3-dimensional region. Which we'll often call it solid. We'll refer to it as a solid. So kind of think of it as a piece of solid. And the integral, let me just write here. So the integral, the integral of the function f of xy dA, this will be the notation for this integral, over this rectangle. Let's call this rectangle R. So this is R. Will represent the volume of this solid. So you see, all dimensions get bumped by 1. Here you have the function in one variable. So the bottom of this picture is one-dimensional, it's an interval. But the region is two-dimensional. And it's represented by a single integral. Whereas now, you have a function in two variables, so instead of one, you get two. You have a three-dimensional region, or solid. The bottom of this region is a rectangle in your original variables x and y. And the volume of this three-dimensional object, three-dimensional solid, is represented by a double integral, which is denoted like this, where dA sort of stands for the elementary area, just like dx was notation for sort of the elementary length. Okay? So this is notation. This is notation which we'll use. And what I'll explain now is the first aspect of the story, which is what does this integral represent? This integral represents the volume of the solid, provided that the function is above the xy plane. But again, that assumption we can make without loss of generality, because any function can be made so by adding a sufficiently large constant to it. Okay. Now the second aspect of the story. How do you actually define it? And again, it's very much parallel to the definition here. You break this solid into smaller pieces. To do that, you first break the rectangle into smaller rectangles by choosing some step delta x and delta y. Right? So you kind of make a grid of rectangles with sizes delta x and delta y. And for each of these very small elementary rectangles, you draw. Let's do this one. See? For each of them, you draw a sort of skyscraper, which goes all the way up to the graph. You see? So that's sort of like a skyscraper which sits at this cell of this grid. And then for each of them you do the same. And then the point is that the entire volume can be approximated as the sum of volumes of those skyscrapers. So this is precisely analogous to what we did in the one-dimensional case. Except now, instead of in the one-dimensional case, the bottom was like a little interval, and now the bottom is going to be a little rectangle. So there will be sizes delta x and delta y. But otherwise, it looks exactly the same. You see, and so here is going to be the height of this is going to be, let's say, if this is the point xi, yi in our partition, the height will be the value of the function f of xi, yi. And so now we just use the same formula, except it's no longer area, it's volume. And it doesn't depend just on I, but it depends on I and j. So I actually should have said yi, xi, and yj, the ij cell of that grid. So that would be volume ij. And this would be f of xi, yj times delta x times delta y. And when we take the sum of all of these volumes, where n and m go to 0, n and m being the numbers of partitions for x and y, we will get a double integral. We will get our double integral. So exactly the same idea. Approximate by sum of volumes of this very thin skyscrapers, and when the partition becomes finer and finer, this sum will tend to the actual volume, provided that this function satisfies some natural properties, like being bounded and continuous. So that's the definition. But again, we're not going to use this definition to actually compute things. Right? We want to use a much more powerful method, like the method which we have. What is that? I have to be careful when I open the boards. You never know what's behind. So we want to use a more powerful method for computation, like the fundamental theorem of calculus. In other words, we would like to do it by taking some antiderivatives of some sorts, right? And this is what I'm going to explain now, the computation. Any questions so far? Yes?
Would there be any comment on the I equals 1 comma j comma?
Very good, that's right. Thank you. I didn't, right, so actually it's going to be double summation. That's actually a very good point. I'm glad that you point this out, because this illustrates more clearly why it should be a double integral. Because this is really a double summation. Why is it a double summation? Because it is a summation over little rectangles in this grid. So this grid actually looks like this. So there will be 1, 2, 3 up to n along this side, and 1, 2, 3 up to m along this side. And so it's really a double sum. And in the limit, this double sum becomes a double integral. Any other questions? Okay. So now we talk about how to compute this. And we again take as a hint, we take the formula from the one-dimensional calculus, which is that we essentially have to take the antiderivative of our function. But if you have a function in two variables, it's not clear which antiderivative you should take. Because actually there are two functions. Sorry, two variables. When we talk about derivatives, we saw that there are actually two partial derivatives, with respect to x and with respect to y. Likewise, there are two partial antiderivatives. You can take the antiderivative with respect to x and with respect to y. And the point is that there is actually an analog of this formula in which you actually have to do both. You have to first take the antiderivative with respect to one of the two variables, and then antiderivative with respect to the second one. And that will give you the answer. So that's the idea. So let me explain this. So the computation is given by the following formula, that this integral f of xy dA over r can be written as what's called iterated integral. Iterated meaning that we do something in one after another, a certain procedure after one after another. We iterate a certain procedure. And that procedure is essentially taking the antiderivative, which we should do twice because there are two variables, right? So it's sort of very reasonable. And so the way it works is the following. We first take the integral of f of xy with respect to the variable x, say. And so the limits will be a to b. So we take this integral assuming that y is a constant. This should remind you of the notion of partial derivative. So in fact, when you do that, you will use, for this, you will get, you can express this as the difference of values of certain function points b and a, and that function will be nothing but the anti-partial derivative with respect to x of this function. And as a result, you will get a function depending on y, because think of this as a family of integrals depending on y. So you have integrated out x, but y still remains as a parameter. So the resulting object is a function of y. And then you just integrate the function of y from c to d dy. So that's called iterated integral because you iterate the procedure of taking antiderivative or doing a one-dimensional integral. But you could also do it in the opposite order. So in that sense, it's kind of reminiscent of the Clairaut theorem, which told us that we can apply partial derivatives in any order and we'll get the same result. Likewise, here we're doing partial antiderivatives, and we can apply them in either of the two possible orders, giving us the same answer. So that would mean that first we integrate out dy. As a result, we'll get something which will depend on x. So in this integral, y is frozen, and x is a live variable. So we're integrating, but then after we integrate it, we start remembering about y, and we get a function of y, which we then integrate. Likewise here, y is the live variable, which we integrate, but x is a parameter. When we make this integration, we get something which depends on x. It's a function of x, which we then integrate itself with respect to x. So these are two different formulas for the same integral, and depending on the choice of the order, first x then y, or first y and then x. And the fact that you can write the integral like this is what's often referred to as the Fubini theorem. Again, this is something which we are not going to prove, but we're going to use it in practical calculations, just like fundamental theorem of calculus. We didn't really prove it, but we use it extensively to actually calculate one-dimensional integrals. So let's see how this works in practice. Okay. Okay, so let's do this example. Say, suppose that R is the rectangle where x is from 0 to 2 and y is from 0 to 1. And the function f of xy is x cubed y cubed plus 3x y squared. Okay, so we want to compute the integral of f of xy dA over this rectangle. And I'm just using Fubini's theorem, so I have to choose which way I want to integrate, which variable goes first. And let's say I want to do first the y variable. So that means that first I do the integral 0, 1, from 0 to 1, x cubed y cubed plus 3xy squared dy. And then I do the integral with respect to x from 0 to 2. Now, it is tempting to just continue this formula, writing this formula. But then you have to carry with you both integration signs and so on. So this is a sure way to make mistakes. So I think it's much better to do the first integral, do the inner integral first, get the result, and then substitute it into the formula. It's a much more straightforward way, I think. You'll see it yourself when you work on this. So let's do the inner integral by itself. It's x cubed y cubed plus 3x squared xy squared dy from 0 to 1. Use the fundamental theorem of calculus and assume that x is just a scalar, it's just a constant. So we have to take the antiderivative of this, right? What's the antiderivative of this? The antiderivative of y cubed is 1/4 of y to the 4th. And this is just a constant for now. We have frozen it, just like when we were doing partial derivatives. So just carry x cubed. Next, take the antiderivative of this, again thinking of x is a constant. You get x y cubed. And now you have to evaluate at 0 and 1 and 0. So you get 1/4 of x cubed plus x. Right? And now substitute it back. We have now calculated the inner integral, so let's just put it in, let's substitute it in this double integral. So we'll get 1/4 x cubed plus x dx. Right? So we get 1 over. So now that's just easy. So that's just the usual way. So that's going to be 1 over 16 x to the 4th plus 1/2 x squared from 2 to 0. Right? So that's going to be 16 over 16. That's 1 plus 1/2. So that's 3/2. Sorry, plus 2. 3. That's things. Okay? Any questions? Yes? Single integral. The question is why do we write it as a double integral? Oh, you mean the notation for dA or for this? I see. So the question is why do we use this notation?